In the last lesson, we learned about Archimedes' principle, the idea that the volume of an object can be determined by measuring the volume of whatever it displaces. Sometimes it's easy to measure how much is displaced. For example, when you displace water, you can capture the water and measure its volume. Right now you are displacing air. And Archimedes' principle goes along with the idea of buoyancy, and that is that whatever the weight of the fluid that you've displaced, whether that fluid is air or water or something else, the weight of the fluid that you displace equals the buoyant force buoying you up, pushing up in the same direction as a normal force. So obviously when you displace air, the weight of the air you've displaced is not very much, and we usually disregard it. When you get into the water and go underwater, you're displacing water, which of course is denser than air, and the volume of the water you displace is much more substantial. Therefore, the weight of that water that you've displaced is more substantial, so the buoyant force pushing up on you is more substantial. We're going to keep these ideas in the background as we move into the discussion of fluids, rather than being stationary as they have been so far, and then you just displace the fluid, or some object displaces the fluid. Now we're going to talk about the fluids in motion, moving from one place to another. And when fluids are moving very, very smoothly, we say that they are streamlined, or we say that there is a laminar flow, laminar meaning flat and smooth. A laminate, for example, might be some thin material like formica that you might cover a piece of plywood with to create a surface countertop. So streamline or laminar means that the particles are moving from one place to another along a smooth path. It is streamlined, and streamlined means you have minimal air friction or water friction, depending upon what the fluid is that the object is going through. If your car or your boat is streamlined, your airplane is streamlined, it's going to reduce the air friction and it's going to improve the gas mileage. It's also going to create a more comfortable ride. The opposite of being streamlined is to be turbulent. Turbulent means that at some point you reach a velocity where you get all this bouncing around because now that air is moving irregularly over the surface. It's having trouble keeping up with your speed and being displaced as you plow through your fluid. You often create these little eddy currents. Maybe you recall seeing a movie where an astronaut or astronauts are blasting off, and initially their ascent off the surface of the Earth is pretty smooth, and then they start going faster and faster, and they seem to be bouncing around a lot. They're encountering that turbulence. If you look at this picture here on the right, you can see the smoke rising from this burnt match, and initially you have your laminar flow right here, nice and smooth, but as the gas or the smoke spreads out and begins to rise, you see here there's a little bit of curlicue as you begin to encounter some turbulence, and then you get some more turbulence, and then the overall movement of this is creating a big eddy current right in there. So you go from laminar flow at the bottom to turbulent flow at the top. Now, when we talk about fluids, we're also going to be using an important word called viscosity. Viscosity we often think of as being the thickness or the gooiness of the fluid. Air would have a very, very low viscosity, near zero. Tar would have a very, very high viscosity and hardly flow at all, it would seem, especially if the temperatures are colder. Viscosity is a measurement of the degree of internal friction in the fluid. And some of that internal friction would be the difficulty of the molecules that make it up to move past each other, which means, therefore, they must be connected by intermolecular forces, IMF, that are holding these molecules together. and it takes more and more energy to separate them. Certainly with oils and gooey things, when you heat them up, they get runnier and runnier as you begin to overcome those intermolecular forces, and the internal friction declines and the viscosity goes down. Examples of very viscous liquids would be crude oil, molasses, maple syrup. Some syrups are very, very thick and gooey, and others are thinner. I've been at my in-laws when they were still alive. We'd take the family up in spring break, and if the syrup, if the sap was running in the maple trees out in the reservation and in the country where my wife's parents lived, they would tap the trees, and this very runny maple sap would flow out, and they would boil it down, and it would get thicker and thicker and thicker, so you can have varying degrees, varying viscosities of your maple syrup or corn syrup. And of course, we've got all kinds of vegetable oils as well. In your car, you might use 10W40 motor oil, or 10W30 or some other motor oil. We want the thicker oils down south where it's hot, and increased temperature causes the oil to get runnier. And up north, you want a thinner oil. That thinner oil is necessary because it's cold for much of the year, and you don't want the oil to become so thick and viscous that it's having trouble lubricating the place where the piston moves in and out of the cylinder. Now here's a wind tunnel where smoke has been produced and from various jets, and you're able to study whether or not the flow of air as your vehicle moves through the air as it's traveling forward is going to create turbulence or not. Of course, here our car is stationary, and we make the wind move very, very fast. Out on the highway, you might have very little wind, but because the car is moving so fast, you get the same relative motion between the air and the car. Now, you might recall from chemistry, we talked about an ideal gas, and we'll talk about ideal gases a little bit later. But an ideal gas, you recall, could be represented by PV equals nert. And if you don't remember that, we'll review that a little bit later. In any case, we also have an ideal fluid. An ideal fluid would be a fluid that, for all intents and purposes, has zero internal friction. We would say it's non-viscous. The fluid is incompressible. Most fluids, it's very, very difficult to compress. If you push on the fluid in one place, it's going to bulge out or move to some other place. In other words, you can't increase its density by compressing it. Number 3, the fluid motion is steady. It's going to be laminar. That means that the velocity, the density, the pressure at each point in the fluid isn't going to change as it goes from place to place and from time to time. And then finally, the fluid moves without turbulence. We have no eddy currents. Now we're going to mention eddy currents again second semester when we talk about electricity and the resistance to the flow of a current, the movement of a current or a charge through a wire. And there are these eddy currents that are the movement of electrical charge, which is very different, but a similar idea. Now, because we're talking about charge and not an actual fluid. All right, let's begin with the equation of continuity as we get into the math. Now, the equation of continuity is based upon this idea right here, that mass has to be conserved. So as a fluid enters a pipe or a hose or a straw or some type of conduit, the amount that comes in has to equal the amount that exits, no matter how skinny or wide the pipe or the hose happens to be. And to a great extent, we can talk about creeks and streams and rivers. Sometimes a creek or stream And maybe you've been canoeing, you've been on different rivers in the Missouri, like the Merrimack or the Current, and sometimes the water enters a narrow channel, in which case, as it enters a narrower channel, it has to flow faster because more water is coming in behind it. And then whenever the narrow channel widens out and it becomes wide and broad, then the water slows down greatly. In other words, we see that there's a relationship between the cross-sectional area of the channel and the velocity of the current going through that channel. Now, as we move forward, we want to be careful that we distinguish between volume and velocity. Notice that little lip or wing that I put on the lowercase v to distinguish it from volume. So that would be velocity. Some context, you don't have to worry about it. You'll notice that in the script of the printer for this textbook, your little lip or wing is on the left side, and I usually put it on the right side. A lot of people do. In any case, another thing that you want to remember is that density is defined as mass per volume. You know that, but you're going to see mass usually written as density times volume, or to use the Greek letter, rho times volume. So you're going to see an awful lot of density times volume representing mass. Another thing that you should remember is that volume equals area times thickness or distance. And so a lot of times instead of volume, you're going to see area times distance or area times height. So just get used to that in this section. So when we look at this equation right here, you see your density times your area. And if you remember that density is mass per volume, and you're multiplying by area, you're going to have your mass per some distance or length represented there. And then we're multiplying by the velocity, and the velocity is a distance or length per period of time. And so when everything cancels, you see that the mass of your water per time that is entering a hose or a pipe or reaching a certain point in the river has to equal the mass per period of time that exits. If not, the mass of water is either going to pile up if it can't get through fast enough, or it's going to be spread out. So this is an idea of conservation, if you will, of mass. Mass is conserved because the mass entering each period of time has to equal the mass exiting. And so we can simplify that equation here and therefore say that the cross-sectional area and the velocity are inversely proportional. So if you have a big cross-sectional area, a big wide pipe or hose or a wide open channel, the velocity is going to be rather small. And when you go into a much narrower channel or skinnier pipe or skinnier hose, the velocity has to increase in order for all the water that's coming in to equal the water that is exiting, using water as the fluid in this case. And we call this the equation of continuity. So the way that you would say it in words is the product of the cross-sectional area of the pipe or hose or riverbed channel and the fluid speed at that cross-section is constant. It always equals the same value. Another term for your cross-sectional area times your velocity is called the flow rate. That flow rate is constant all the way through. And here are a couple examples. Down here we have a skinny pipe. Up here we have a pipe with a much larger opening. And down here on the left, we have a small cross-sectional area. So we're going to have a bigger velocity as the water has to get through to make way for more water coming in. Over here on the right, we have a larger cross-sectional area, so the water does not have to move as fast, and we have a slower rate. That's not a good-looking velocity, so I'll fix that. And then when we look at the hose, a spigot or faucet of water, you'll notice that up here we have a very, very large opening or cross-sectional area of water. Down here, it's very small. Therefore, the speed of the water at the top is not as fast, but the speed at the water at the bottom is going a lot faster. And you're all familiar with maybe watering the garden, watering your lawn, watering a freshly planted tree or flower or bush. You know that when you put your thumb across the opening of the hose, that you have now reduced the cross-sectional area from larger to smaller. You've covered up part of that opening. And therefore, the water, which was coming out rather slowly, now is going to come out much faster, which means it's going to go farther. And you're going to be able to reach more distant objects with water from the hose. By the way, looking down here, that's the speed of the smoke. As smoke rises, and you saw that in an earlier picture, as the smoke rises, the speed is going to increase, the cross-sectional area is going to decrease. And the stream soon reaches a speed so great that the streamline flow is not possible. No longer can you have a smooth laminar flow, but now there's a lot of turbulence. And the relationship between the speed flow and the turbulence is something called the Reynolds number, which we get to in a later section of this chapter. Looking at the example of Niagara Falls, I don't know if you've ever been there. I've been there twice now, once as a boy and once when my kids were younger. It's pretty magnificent waterfall. Nowhere close to being the tallest waterfall in the world, but it's one of the waterfalls that dumps the most amount of water in a short period of time over the cliff, where there's a fault line in the Earth's crust there. So we've estimated that over 5,500 meters cubed of water is going over the 670 meter cliff. That's just the Horseshoe Falls. I believe that's the falls, I could be wrong, that you see from the Canada side. There's more of the falls that you see from the American side. It's not quite as spectacular, which is why everybody goes to the Canadian side to look at the falls. And the water, when it goes over the edge, is only 2 meters deep, about my height, or I'm a little shorter than that. So we would say, what is the speed at the moment it's going to go over the cliff, go over the edge? And so we need to find the cross-sectional area of the water, and the cross-sectional area of the water is going to be the width times the depth. And this gives me the cross-sectional area. So if this is the cliff right here, and you can imagine that the water that's getting ready to go over the cliff has a cross-sectional area of 1,340 meters squared. And then we can find the flow rate. We put the flow rate in here, and we put the volume of water. Volume, notice it's meters cubed, so this is going to be volume. The volume is going to be right here. So here's my A, and here's my, this is the volume per period of time. So it's the speed of that volume. And we get a speed of 4 meters per second. Let's see, I want to double check that. area times, yeah, here's the velocity right there. And as you know, area times meters per second, which is velocity, gives me my volume per second. Solving for V, we get 4 meters per second. This is an interesting medical question. What happens to the speed of blood in an artery when plaque starts to build up on the artery side? So if this is the wall of the artery and you get some plaque building up here, you can see if this is a vector representing speed, the speed has to increase when the channel of blood is narrowed because of the plaque, and then it's going to slow down again. And of course, where the speed increases, that can create all kinds of problems. We're going to learn a little bit later that it produces a lowering of the pressure, which causes the blood vessel to begin to collapse, restricting flow. There's all kinds of issues involved there. Also, that speed might dislodge pieces of the plaque. And if those pieces of the plaque then are carried along and get clogged up in some capillary somewhere, that can be very, very dangerous and cause blockages. Watering a garden, same idea. We illustrated this before. So we have a water hose. It's 2.5 centimeters in diameter, and it's used by a gardener to fill a 30-liter bucket. The gardener notices it takes 1 minute to fill the bucket, and I'm sure you're just like me. We stand there looking at our cell phone or our watch to time how long it takes to fill up the bucket or the watering can. And then we have a nozzle with a much narrower opening, 0.5 centimeter squared, as opposed to 2.50 centimeters squared. In other words, we're reducing the size of this cross-sectional area by 1/5. We project it horizontally, and we're 1 meter above the ground, probably holding it down below our waist. And over what horizontal distance can the water be projected? So the first thing we do is we calculate our volume flow rate, and our volume flow rate is going to be, here's my velocity of 30 liters per minute, and all of this is how we convert our cross-sectional area. We're going to have we're going to have our, let's see, we have centimeters cubed, and this is centimeters cubed. Notice the 3 there, so the centimeters cubed cancels out. And we have our 1 minute, which is the same as, wait a minute, I think that's 1 meter, my bad. Let's erase that. You can see that we have a conversion factor of 60 seconds per minute right here. And this is 1 meter cubed, which cancels out my 1 liter. Oh, I'm sorry, we converted our centimeters cubed into meters cubed. And because we have meters cubed per second is going to be left behind. There's the liters. There's where the liters cancel. Liters cancel, centimeters cubed cancel, and we end up with meters cubed. Remember the 3 was there outside the parentheses. And we get meters cubed per minute. The minutes also cancel. There we go. 5 times 10 to the minus 4th meters cubed per second. We're going to take that number and come over here and plug it into our continuity equation right there. And of course, we're going from big area, small velocity, to small area, big velocity. We solve this for that velocity right there, and we get 10 meters per second. And that's the velocity of the stream exiting the hose, a lot faster. And then we can pull out our old kinematic equation from way back in, chapter 3 or so. And we can calculate the time it takes for the stream to fall 1 meter using kinematics. And we're going to plug our numbers in. Our gravity, of course, is 9.8. We've solved this equation for t. And our height is 1 meter, which is y. The reciprocal of 1/2 gives us that 2. And we see that it's going to take almost half a second for the water to fall. And so you might remember that this simplifies to distance equals 1/2 gt squared. Doesn't matter whether it's water or a rock or anything. It doesn't matter whether it's moving horizontally or just dropping. The horizontal component is independent of the vertical component. So the vertical component gives me 0.452 seconds, and we plug that in here, times meters per second. My seconds cancel, and we see that the water is going to be able to go about 4.5 meters, maybe about 15 feet or so. All right, Bernoulli's equation, named after a guy named Daniel Bernoulli, who was one of those guys that had a rough background growing up, and I'll mention why in a minute, but was a brilliant thinker in all kinds of different disciplines, especially mathematics and theology. He was a devout Christian. He was what you would call a Calvinist. I would call myself a Calvinist, and I would say that would be pretty typical of our faculty, in that Calvinist is somebody who pretty much agrees with the ways in which John Calvin, way back in the early years of the Reformation, articulated the central doctrines of God's Word and God's sovereignty. And this is very relevant to Reformation Day, which some people have unfortunately turned it into Halloween, which of course is a word which used to mean hallowed eve or holy evening before All Saints' Day. All Saints' Day on November 1st was when we celebrated and remembered and reflected on the sacrifice of so many Christians over the years who were tormented, persecuted, and even martyred for their faith. And we remember them, or at least we should. Anyway, John Calvin, some of the ideas of the way he summarized God's total sovereignty is to use the word tulip, a good Dutch term for the fact that T would stand for the fact that every human being who's ever lived is totally depraved in our thought, word, and deed. We are basically evil and sinful, not basically good, like so many religious systems believe. And then the U in tulip would be unconditional election, or the idea that God is totally sovereign over how his Holy Spirit is going to work in an individual's life. And then the L is limited atonement, meaning basically that God's blood, Jesus' blood, shed for the remission of the sins of God's children, is totally sufficient to accomplish making them perfect in God's eyes and satisfying divine wrath. Limited atonement, irresistible grace, letter I in tulip, where the Holy Spirit pursues God's children and draws them to himself. It's through no work of our own. We're not saved by works. We are saved entirely by God's grace through his Holy Spirit. And then letter P in tulip, perseverance of the saints. And that is that when God saves his child, nobody can undo what God has done. Nobody can, to use words of the Apostle John, pluck them out of God's hands. Sometimes you hear of somebody who abandons their Christian faith or deconverts, which usually means they were never a Christian in the first place. All right, having talked a little bit about Bernoulli and the fact that growing up, because he was a Calvinist, the Roman Catholic Church after the Reformation persecuted a lot of Calvinist communities and pushed people from their homelands and from their cities. And eventually he ended up with his family in Switzerland. Okay, let's get back on track with some of his work in physics as opposed to theology and mathematics. He often explained the final basis or foundation for his physics and math principles using theology, using a sovereign God. So, using in Bernoulli's principle, we're going to assume again that this is an ideal fluid, that it's incompressible, it's not viscous, it's non-turbulent, and as it flows through a system, here's our equation for work right here, which you know is force times distance, moving in the same direction. We don't need that cosine theta at the end. And my force is pressure times area. If you remember, pressure is the force per unit area. So therefore, my force becomes pressure times area. And then the next thing you should notice is that area times distance is going to be volume. So we can define the work being done as the pressure times the volume right here. And that pressure times the volume is going to be constant all the way through a pipe or a hose, like the equation of continuity. And so this work is going to be part of the conservation of energy. Before we had the conservation of mass with the principle of continuity. Now we have the conservation of energy with Bernoulli's principle. And the energy is going to be conserved as the fluid, the ideal fluid, goes through the pipe or the hose. And therefore, all the different kinds of energy, be it kinetic energy or potential energy, or the work being done by the fluid, is going to be, when you add all that up, it's going to be the same all the way through. If you do have some friction along the sides of the pipe, but not so much there, because we're talking about an ideal fluid, but if there's an increase in height or decrease in height, or if there's an increase in speed or decrease in speed because the pipe or the hose gets wider or narrower, energy is going to be conserved, of course. And the one way that you can look at this is that all the energy that you start with, the kinetic energy of your fluid as it enters that specific spot on or location of the hose or the pipe or the river channel, the water speed is going to change one way or the other. You may be going up or down relative to your starting points. You're going to have a change in potential energy. You could, if it's not perfectly flat. And then there's going to be the work that needs to be done. NC for non-conservative that you've seen before. And we can rewrite that in a more complicated way down here. Our change in pressure times volume, our change in work, is going to equal our change in kinetic energy plus our change in potential energy. If you remember that potential energy and all have mass in there, you're going to see that that's going to cancel out a little bit, especially when you recognize over here that density is mass per volume. And so therefore we can rewrite our pressure. Let's see. Our mass is going to equal our density times our volume. Remember, this is what's supposed to look like the Greek letter rho for density. Capital P is supposed to be for pressure. Got to keep that straight. This is pressure way over here. Your masses are going to cancel out. And so we're going to get this equation right here. We're going to divide through by the volume. And when we divide through by the volume, that gives us this change in kinetic, a form of kinetic, and our change in potential. And we get our Bernoulli's equation right here, which I forgot to highlight. There we go. And basically what we're saying then is that your pressure and your kinetic energy per volume and your potential energy per volume all the way through the pipe or the hose is going to be the same throughout the path. It's going to be a constant. Now we can see this with various experimental devices. We can demonstrate it. For example, if we have a Venturi tube, and this Venturi tube, which is pictured right there, this Venturi tube, you'll notice that we have a wide opening right here, a restricted opening there, a wider opening there. That means if we're going to be looking at the speed of the water has to be greatest where the opening is the least and not as great on either side. Just like down here where the cross-sectional area is small, we have a low speed where it's greater. Where the opening is narrower, the speed has to be much greater. In other words, your speed is going to be inversely proportional to the cross-sectional area. That's a summary of Bernoulli's principle. And you can see that you get these differences in pressure. We can also say, therefore, that your pressure is going to be inversely proportional, therefore, to the speed. And let's make sure we get the tail on that V. So you can see that where the speed is the greatest, we have the least pressure. So I'm going to put a circle like a low pressure system. We have our lowest pressure there, and so the liquid is going to come up toward in the direction of where the pressure is lowest. Where the speed is slower, we have the greater pressure. So we high pressure here, high pressure system there, and therefore, since the pressure is greatest there, acting down, these heights are the least. Over here, you can see it again. We have high pressure where the speed is lowest, and we have a lower pressure. The gauge is farther counterclockwise where the speed is the greatest. So here's a shootout at the old water tank. I don't know if it's ever happened to you yet, but it happens all the time in physics where you're shooting your trusty six-shooter at a bad guy and you miss, unfortunately, and you hit the water tank and then the water drains out, and you hate it when that happens, though the rustler doesn't. In any case, we might ask ourselves the question, how fast will this water be coming out of the tank based upon how high up on the tank the hole in the tank is, and when that water does come out of the tank, how far from the base of the tank does it travel? And so that's what this problem is all about. And so when we look at our energy that we have to begin with, we have this initial potential energy right here. This time it's on the right side of the equation instead of the left. But the potential energy is going to be gravity times how high up the water is. So my value of y there is the letter h right here. So we have the height of the water above the hole. The height of the water above the hole, not the height of the tank. So that's how much potential energy we have, to use that term in a more general sense. And then where does that energy go? Well, all of that energy goes, if we have an ideal fluid for the most part, it's going to go towards having less potential energy because you're farther down the tank, and you're going to also have a kinetic energy per volume. And so when we cancel out the density of our water, we get this equation right here. And let's see here, I don't know why I have the tail on here when this says volume, but so that we're talking here about velocity. So when we solve this equation for our velocity and putting in the fact that the hole is a ½ meter below the surface of the water, we see that the speed coming out the side is 3.13 meters per second. let's see here. Next, use the displacement equation to find the time. And you've seen this equation a bunch of times before. And so we have our distance equals 1/2 gravity times squared. And we plug our numbers in. We find out that whether it's moving horizontally or just falling vertically, the amount of time it takes to hit the bottom is the same because the horizontal and vertical components are independent. It takes 0.782 seconds for the water to fall. And so we plug that in here, and we have our horizontal speed this way, and the water is going to shoot out 2.45 meters. Now, this is an interesting comment down here about Torricelli's law, another Italian. And Italians figure prominently in the study of fluids and pressure, if you remember from chemistry. And if we take this equation right here, which came from the equation that my final velocity squared equals the initial velocity squared times 2gd. And then we take the square root of both sides. Initial velocity is 0. We get this equation down here. And we solve for the velocity, and we get the same answer, 3.13 meters per second. So the speed of water emerging from the hole is equal to the speed acquired by an object falling through the vertical distance. And finally, in this screencast, fluid flow in a pipe. We have a large cross-sectional area here. We have a narrower one down here. So we have big A, small v. Down here we have little a, big V. And our Bernoulli's equation is going to be right here, where my pressure has got to be the same all the way through. So all the components of that pressure, we got 3 of them right here, must equal each other when you add them up all the way through. This pressure, air pressure in this case, air pressure is going to be constant, so we can cancel that out. And so we have the pressure due to the kinetic energy and the pressure due to the potential energy. And again, my density is going to cancel out. And eventually this whole thing boils down to this equation right here, which is what we've been talking about all along, like right there. And we basically plug our numbers in and solve for the velocity, and we get the speed of 11.4 meters per second. Now, there are a lot of great examples of Bernoulli's principle, and we'll look at that in a separate screencast.